Hi class, Mr. Morris again. We're doing another set of notes today. Unit 5.5 collision model. This is kind of similar in a way to collision theory, which we talked about in terms of gases. But we're talking about how the collision model affects the rate of the reaction. For an elementary reaction to successfully produce products, the reactants have to successfully collide in order to initiate bond breaking and bond making events. So that means they have to collide in such a way that the bonds can be broken and then new bonds can be formed. The collision theory states that when suitable reactant particles collide with each other, only a small fraction of the collision leads to a reaction. These are called successful collisions. So it's just a small fraction of the collisions that are actually successful. The successful collisions have two requirements. They have to have sufficient energy to overcome the energy barrier needed to initiate what we call bond breaking events. We've got to break those bonds in the reactants in order to make this reaction happen. Also, proper orientation has to occur between the reactant particles that allow the bonds to rearrange in a required manner. We're going to go through both of these with some detail in a little bit. Pause the video and click the link that's given to watch this fairly short video by Michael Farabaugh that explains collision theory in a little bit of a different way and also gives some tips on how to study chemistry. All right, once you've finished that video, we're going to continue. The essential components of collision theory are that particles must collide. Most often, only two particles may collide at one time. Collision between three particles, we mentioned this in the last video, but collision between three particles are extremely rare. That's why it's very rare to have a termolecular mechanism step or elementary reaction. Proper orientation of colliding particles is essential so the molecules come in contact with each other to form products. The collisions must also occur with enough energy to start the bond breaking. And this is kind of how that happens. It has to have enough energy to overcome the repulsion of that outer shell of electrons. Remember, electrons repel each other, so when two molecules get close to each other, they've got to come with enough energy to overcome the initial repulsion that they're going to feel. So they have to hit hard enough to overcome that. They also have to have enough energy to transform that translational energy, which is the energy of just motion from one location to another, to translate that translational energy into vibrational energy so that they can penetrate to each other so the electrons can rearrange and form new bonds. So you've got to have enough energy and it's got to be oriented the right way. The activated complex, this is an important term to know, the activated complex or the transition state, which we're going to talk about in more detail throughout this unit, is the arrangement of atoms as the reactants are transforming to the products. So it's this intermediate transition state when they are changing from reactants into products. The bonds are breaking and new bonds are forming at that moment where it's halfway there, basically. If you look at the diagram down here, this is the transition state. Okay, so the molecules have collided and they're in the process of transforming into different bonds. This is the transition state, which I'm circling right now with my cursor. All right, it has higher potential energy than those of the reactants and the products. So if you were to look back at our last set of notes, you would see that the energy diagrams where you've got the little bump, okay, the top of the bump is that transition state. It's a higher potential energy. So this is just kind of a particulate look at what we're talking about. If the reactants are moving too slowly, they're just going to bounce off. There's no reaction. You started with NO3 and CO, and you ended with NO3 and CO. They just bounced off of each other. They weren't moving fast enough. Now this time they're moving fast enough maybe, but they're just facing the wrong way. What we're trying to make is CO2. All right, so if the oxygen side hits this molecule, it's just going to bounce off and we'll still have CO and NO3. But if it's rotated such that the carbon is bumping into the oxygen and it hits with enough energy, then the bond between nitrogen and oxygen can be broken and the bond between carbon and oxygen can be formed, and we'll end up with NO2 and CO2. This is just an example. And then again, this is another look at it that shows the transition state. The molecules bump into each other, and for a moment they're all kind of clumped together before these bonds are split so that we have two AB molecules. But if they're colliding like this, you can see that they're just going to bounce back off of each other and you'll end up with the reactant particles. Again, no reaction occurs. All right, we have a Maxwell-Boltzmann distribution curve right here, just to remind you what we mean by Maxwell-Boltzmann distribution, and maybe you've forgotten that term. That's okay. A Maxwell-Boltzmann distribution curve just shows the percentage of molecules at any given kinetic energy. So this is all at a specific temperature. At a specific temperature, the average kinetic energy is right around here. Okay, it's a little bit to the right of the top of the bump. Okay, but we've got some molecules that move much slower and some that move much faster. That's the general idea. This is the percentage of molecules at any given kinetic energy. Well, the Maxwell-Boltzmann distribution curve, learned about in Unit 3 with gases, describes the average distribution of kinetic energy of the reactant particles. So just the distribution over this whole thing. Only particles with energy greater than the threshold energy, which is labeled on this graph. See that threshold energy? That's the energy that's required for a reaction to occur. So only particles with energy that is greater, further to the right, than the threshold energy will have the ability to have successful collisions. And that's this little red section here. Those are the only molecules that have enough energy to collide hard enough to react. All right, that kind of wraps up the first two sets of notes. Watch the AP Daily video talking about Unit 5.6 notes, and we'll talk to you again next class. Let me know if you have any questions.